I will start with a short introduction about the motivation and background about of the CAD integration, then recall and review some general remarks on geometries in Permas, and then later I will continue with the, let's say, main event, the CAD geometry creation in chapter 3, and finally I will sum up and also give a little bit an outlook about on next steps of development. As you heard in the morning from the presentation of Dr. Helfrich about 40 years of innovation and service, you know that since a long time Permas has an integrated topology optimization capability, and during that time, also due to my contribution, not only my contributions, but maybe also a little bit, topology optimization has grown to a certain maturity that leads to the ability to establish what we call design by simulation process. You see an example on the right side where we have an FE model of a design space doing topology optimization with clear results and also with considering manufacturing restrictions, and finally get a result that is at least close to a manufacturable design. So this leads to the demand that topology optimization is often demanded to be used as a tool for generative design. So I don't like too much buzzwording, but generative design, I think, is a well-established word that means that topology optimization should be used for an automated generation of part designs. Now, state of the art is that smooth topology optimization results after we have smooth results, and they are represented typically as tessellated surfaces, typically triangle surface meshes, and later then exported in STL format. This has not only two main drawbacks I will mention here. One is that this representation of the results of a topology optimization this way is inexact. This may be acceptable for free-form surfaces, but definitely not as a representation of a part design for functional surfaces, just as flanges or bearings or boreholes and so on. Next drawback, also very important, is that if you have surface geometry representation by a huge number of triangles, this is a hardly editable kind of geometry representation, hardly editable in a final processing step. This leads to the necessity that after topology optimization, usually a design engineer needs to do a complete reconstruction of the design proposal in his CAD system. And this is the motivation why we try to achieve CAD integration, because CAD integration of topology optimization should overcome exactly this limitation. So what we try to establish is a workflow that starts with the CAD geometry of the design space that is created in the CAD system, and then after doing the Permas topology optimization with well-defined results, hopefully then delivers at the end a CAD geometry of the optimized part design that consists on the one hand of the faces of the design space geometry that is not changed because it's on the non-design area. Typically this comprises functional surfaces like already mentioned bearings, flanges and so on that are typically represented by regular surfaces like planes and cylinders and so on. And in addition, adds the new freeform surfaces that involve during the topology optimization process and then should be represented as B-spline surfaces. And of course, this complete process should be integrated in the graphical user interface VisPER. Before I continue with the content, I have to say that to a large amount, the work for CAD integration has been done within a collaborative research project named READI. The topic of this project was the line integration of additive manufacturing in the automotive sector. So additive manufacturing is a very important background for the design by simulation process and for generative design, or for the demand of topology optimization to be used as tool for generative design. And this work was, to our great pleasure, funded by the Federal Ministry of Science and Education, what we highly appreciated. Now, next I want to recall some news from Permas version 19 with regard to the topic geometries in Permas. In version 19, we introduced a data model for boundary representation geometries in Permas as a new high-level data bracket. You experienced Permas user, you probably know that we have a high-level data bracket for the FE model. We have, for example, a high-level bracket for material definitions. We have a new one for definition of functions, and we introduced a new high-level data bracket for geometry definitions. Now, these boundary representation geometries that they consist typically of topological elements like vertices, edges, and faces that are then grouped to shells and solids. The most important thing why we did this integration of a data model for geometries in Permas is that we are able to link the entities, nodes, and elements of the FE component to the entities of the geometry. We are so-called shape references. This is directly comparable what you're doing when you link the elements of the FE model to material properties. In the same way, you can link the nodes and elements of the FE model to the data of the geometry. Other important feature of our data model for geometries is that we can as well as exact or parametric geometries also represent approximate, as we did before, let's say triangulated surfaces, or even mix both types of geometry representations, exact and approximated, in what I mentioned, what I call hybrid geometries. And then in addition, we also added an interface that we not only are able to export triangle surface meshes to STL, but also read and write geometry data in the well-known step format. Also, a new option in VisPER version 19 was the first meshing capability we introduced in VisPER. I don't want to go into details about this because I already told you maybe 2 years ago. The main intention doing this was that we want to be able to create TED models of CAD geometries of design spaces for topology optimization. The main advantage for doing this directly in VisPER that we are able, with our own implementation of a meshing algorithm, that we can automatically link the FE model to the CAD geometry of the design space via the already mentioned shape references. Of course, we want to further developments, we also want to offer let's say, a posteriori linking to CAD geometries for meshes that are provided by external tools, e.g., for example, Meshworks or whatever your favorite meshing tool is. For up to now, we just use the property of our own implementation of a meshing algorithm. Now, with this two basic ingredients, we extended our so-called design wizard in VisPER that generates geometry representations of the results of a topology optimization. Now, first, the result of a topology optimization is basically nothing else than an element selection that is indicated by elemental filling ratios. Now, what the design wizard in VisPER does is that it's does in an automatic process. It first improves this selection, then interprets this element selection as an implicit surface representation or as a discretization of this, then converts it into an explicit surface representation as a triangle surface mesh, and then also transfers the shape references to the CAD geometry of the design space as far as possible, wherever the surfaces remain constant or still contained in the final result, for example, non-design space areas. And then in a final step, we can create this what I called hybrid geometry that consists of the faces of the design space geometry here indicated in red, that are the functional surfaces like planes and cylinders in non-design area, and together with the new free-form surfaces that evolved during the topology optimization as a triangle mesh. Now comes to the next step. What we want to do is to create the final CAD geometry of our result of the topology optimization. When I talk about CAD geometry in this moment, I talk about exact, or other words, let's say parametric surface representation. This means that we need a process to convert the triangle surface mesh into a parametric form, in form of B-splines, as I already told you. And this process of parametrization, of course, is the most challenging part of the CAD integration. And this is a new feature in the new version of VisPER version 20. Now, this process this may be also seen as a reverse process of meshing. During meshing, you convert a parametric surface into a surface mesh. So you cut it in small triangles, and now we do the opposite. The approach we follow for this in our solution consists of two steps. The first step is that we tile the surface mesh into quadrangular patches, and then we use these quad patches to fit CAD-compatible tensor product splines that here in our case we use B-splines. Then, together with the reused faces of the original design space geometry, this results in the desired CAD geometry of the optimized part design. Now, the most difficult process or step in this process is the quadrangulation of the surface. Here we aim to generate quad patches with a moderate number. So this means that we want to keep the resulting geometry editable in a post-processing step in the CAD system. So there's no gain if we have the same number of quad patches than before. The triangle mesh has triangles, so we want to drastically reduce the number of patches. Then we want, like an engineer would do, is we want to align the patches well to the surface shape. This means especially the principal curvatures. And then we need to place unavoidable singularities that occur in such quad layout. These are nodes where less or more than 4 patches meet, like here on the right side, you can see this. They need to be moved on reasonable places. And then we want to avoid, as far as possible, the occurrence of T-joints, as you see here below. So this generation of such a quad layout is done in 4 steps. In the first step, we generate so-called cross field. These are 2 orthogonal vector fields on the surface. The second, we compute a global parametrization. Then third, we trace isolines emanating from the singularities. And then we extract the quad layout. So this is maybe to explain you in detail what all this means. We need maybe 2 hours, but just give you a short impression about what we're doing between 2 user conferences in our development team. So just to give you some insight in our work. The cross-field generation, what we're doing, this is at the end, it's a smooth interpolation between feature and boundary lines and what we call salient directions. This means these are principal directions in highly anisotropic areas, as you, for example, you can see here. And such a cross field, if you compute this, this encodes as well the geometry as well as the topology of the surface, because this also determines the number and placement of singularities. There's a close relationship between number and number of singularities and the topology of a structure. Then the following step is, no, this is not putting the geometry into a pyjama, but this is the computation of a global parametrization. This means first we cut the surface into a topological disk, and then we compute two scalar fields that have gradients that are aligned to the previously computed cross fields. These two scalars that are nothing more than UV coordinates in the 2D parameter space. So why are we doing this? These gradients, per definition, are integrable vector fields, and hence we can trace isolines along this UV coordinates. So when we now trace the isolines along this, we trace the isolines of these coordinates emanating from the singularities. These isolines or these traces only cross orthogonally. This is a first step towards our quad layout. Now the next step is a bit complicated to explain. Maybe you can imagine you have one isoline emanating from a singularity here and going to the right side, and one going down here. Then we try to find here the hypothenuses of right-angled triangles, and if you find the right one and find a complete set of these hypothenuses, then we get a conformal quad layout. We realize this is a bit hard to explain, but it's a kind of optimization that is NP hard. Don't worry about this. We have an approximate algorithm for this that finds a good solution very quickly. We relax this problem by allowing additional T-joints, and then finally we get the desired quad layout. What sounds to you maybe very complicated in this moment, you don't have to worry about this. If you're using VisPER to create a geometry out of topology optimization result, this looks much more simple. So you don't have to worry about the orientation of tiny crosses. You don't have to worry about how to pull a pyjama onto the geometry. You don't have to find the right spaghettis to extract the quad layout. You just press a button and then you get a preview on your mesh input data. This is actually the hybrid geometry consisting of the reused faces of the cut space geometry together with a mesh that should be of the freeform area involving during topology optimization that should be converted into B-spline patches. Then automatically the quadrangulation is generated. You can control it with some parameters that, at the end, this determines the number of patches, how well they are aligned to the geometry, and also how many T-joints are arising. And if you're satisfied with the result, then you click the next button. Together with some smoothing, you get the fitted B-spline patches and then the final geometry. Now, as a result, you can see the comparison before state of the art, before version 20 of VisPER. We have a result of a topology optimization with 70,000 nodes, 34,000 triangles, and typically exported in STL format. With all the drawbacks I already mentioned, now the result is you have a geometry consisting of 29 regular cut faces. These are the planes, cylinders, and so on, that are exactly the same as they were defined by the designer in the CAD system. And then they are combined with a joint with a 168 CAD-compatible B-spline freeform faces, and then together exported in step format. Finally, I want to show you, just to get an impression about the possible application areas, two more examples. On the left side, a car suspension. You know this from the year 2012, I think. We also already presented this car suspension in a result with nearly 50,000 nodes and 30,000 triangles. And now only a half model to maintain symmetry. This results in a step-compatible geometry ready to be transported to the CAD system with only 170 B-spline faces. On the right side, an engine bracket, also a typical application. And you can also see very well that we have introduced an additional smoothing capability during the spline fitting. So at the end, the CAD geometries we create this way are by way not perfect, but they close the gap between the results of topology optimization in our FE world to the CAD system for further processing by design engineer. So let me summarize. The CAD integration that we implemented established a CAD-to-CAD workflow for topology optimization. This means we start with a CAD geometry of a design space, and the result is a CAD geometry of the final design. The interfacing with the CAD software is based on the well-known step standard, and the topology optimization now results in a CAD geometry that merges the reused regular faces from the original design space geometry together with the new free-form faces that are parameterized as B-spline patches. Now, we think with this CAD integration of topology optimization, we've done an important step toward a convenient generative design based on topology optimization. Nevertheless, this is an important step, probably not the final. One open topic is that we want to extend our parameterization also to regular faces. So this may be important if we don't have a CAD geometry of the design space, but just a pure conversion of a surface mesh to CAD geometry is required. This is something we work on with high priority, just to enable more flexible workflows. So this is my last words to the topic, and thank you for your attention and look forward to your questions.
So I expect questions. Yes, please.
Thank you for this good impression of your new features. Question about the difference between the new created CAD model and the underlying points you created on your optimization problem. How far away are the surfaces from the outer shape now? Is there a quality criteria that we can observe?
This depends. You know, this is what I told you. We have during this last step, we have some opportunity for smoothing. So this depends on how the smoothing tolerances you choose. You can stay very close to the triangle mesh, but then with less smooth results. Yeah. Of course, a reanalysis of the result generated automatically by this process is necessary. Nevertheless, I think also even if you give this result, this CAD geometry to a design engineer, he also will do some changes, you know. But you're right. I cannot tell you. This is just a matter of reanalysis of the final design. Every step, what changes the shape is subject or should be subject to a reanalysis.
And another question is of the smoothness of the patches that fit together. Is there a criteria to this, or leave them at the edge that you created alone, so the normals looking in the different directions?
No, we just have a simple parameter, more or less. So we don't have, up to now, we don't have concrete values for normals or deviations. So we just give the user similar to a slider or just a value from strong smoothing to small smoothing. You know.
And for the function that underlying the surfaces, is there a parameter that I can create a surface with 5 grade or 7 grade or 11 grade?
Now we only use cubic B-splines, so they're most common. Maybe in future extensions we can let the user choose this, but for the moment we use only cubic B-splines.
Okay, thank you.
So I have this impression that the symmetry is not giving after the optimization. When you create the patches, although the original design is symmetric, left and right are not symmetric.
Your impression is true, but the model isn't symmetric.
It's not symmetric.
It's not symmetric.
Okay.
But you're right. I show you in this example. So up to now, we have no possibility to maintain symmetry during this process. This is why in this case you see here, I just took the half model, and then later one can do the symmetric model.
Although you cannot do this always. I mean, sometimes you have loads that are not break the symmetry, then you need to maintain the full model.
For the moment, it's the workaround, because up to now we don't have the possibility to enforce the symmetry in this process.
I get it.
This is also something subject to future development.
This will be possible in future, probably.
Hopefully, yes.
Thank you.
But difficult.
Yeah.
More questions from the audience. There, Markus.
Now you have topology optimization, going back to a CAD. For future development, something like to close it in the direction like you have a shape optimization afterwards, your mesh collapses too much, you create a geometry, remesh, and then go on? Is something like that planned, or is that?
Yes. The same process. You don't need the surface mesh must not stem from the hull generation of topology optimization. This could also be the result of a shape optimization.
Okay.
So, is there any question left? No. Then, thank you again, Christian, for your nice presentation.